You've seen gradient descent, and you already know how to implement the basic gradient descent algorithm for linear regression. In this and the next video, I'm going to cover a couple topics on gradient descent in practice, in which I want to tell you about a couple simple methods to help you get gradient descent to run much better in practice. The first of these is going to be the idea of feature scaling. Suppose that, as before, we have a hypothesis of the form like so, with two features, x1 and x2, say, right? Earlier we saw that if you implement gradient descent to solve for the parameters theta 0, theta 1, theta 2 to minimize your cost function j of theta, then the cost function looks like a big bow-shaped function, and if you run gradient descent, we saw this figure with the contours, and gradient descent fairly quickly finds its way to the global minimum. It turns out that this rosy picture applies only to gradient descent in certain settings. And in particular, one problem that gradient descent runs into is if the features are on very different scales. So, in particular, one good thing to do to make gradient descent run quickly is to make sure that the features are on similar scales. And by similar scales, I mean that the feature values take on similar orders of magnitude. So, for instance, for our housing example that we were using earlier, right, x0 was always equal to 1. X1, which was the size, maybe our houses run from a range of 0, well, not really 0, but our houses run up to, say, 2,000 square foot houses was the typical range. And x2, right, the number of bedrooms, that ran from, let's say, 0 to 4 bedrooms is typical, right? So it turns out that if you have some features that take on a huge range of values, like x1, and some values that take on a much smaller range of values, like x2, then if you look at the contours of j of theta, the contours of j of theta will still be ellipses, but the contours may look something like this, where you have ellipses that are extremely tall and narrow and thin. And in fact, the aspect ratio of each of these ellipses will actually have something like a 2000 to 4 aspect ratio if size goes up to 2000 and bedrooms goes up to about 4. So you have this very huge aspect ratio, very long, very, very tiny, thin concentric ellipses. And if you run gradient descent, you find that gradient descent actually a very hard time finding its way to this minimum. In particular, gradient descent will take tiny steps like these, tend to oscillate a lot on its way to try to find the global minimum. And it turns out that even with very, very tall, narrow, elongated ellipses, if you train linear regression with a tiny learning rate, it will still get to the global optimum. But this sort of oscillating back and forth behavior, it can take gradient descent a long time to get to the global minimum, or you might need to use a very small learning rate. Okay, and this is a consequence of if your features are on very different orders of magnitude. So in order to fix this, one thing you can do is just rescale your features. So you can let x1 be equal to the size of the house in square feet, say, divided by 2000, and let x2 be equal to the number of bedrooms, over 4. And if you do this, then you have that x1 and x2 are both, in a similar range of values and lie between 0 and 1. And with this change to the features, you find that the contours of j of theta will look much more like will have a much more reasonable aspect ratio. It won't be those extremely elongated ellipses. And if your contours of j of theta look like this, then wherever you initialize theta, right, it'll find its way to the global optimum. It can find its way to the global optimum much more quickly. Okay, hope this plot makes sense, right? These are the theta 1 and theta 2 axes, say, and these are the contours of the function, the bow-shaped bowl-shaped function j of theta that you're minimizing. So this is sort of a simple rescaling to make the features on a comparable scale. And remember too, right, you have a feature x0, which is always equal to 1. So you want your features to be all on the same scale. So maybe between 0 and 1 or between -1 and 1. It turns out that, don't need to worry if they're on exactly the same scale. If all features have exactly the same range. So long as they're comparable, so long as they're roughly comparable, it should be okay. And so as a concrete rule of thumb, if you have different features, and if one feature is, maybe 2x or 3x, maybe even 5x, the range of a different feature, it should be fine. Is only if you have a feature that's maybe 100 times the range of a different feature, or 1,000 times the range of a different feature, then you should try to rescale them to make sure they're on more comparable scales. Finally, I've been talking about just rescaling the features by dividing. It turns out it can also normalize the mean. So you can take the feature x1 and subtract off some constant from it to make each feature have 0 mean, or approximately 0 mean. And it turns out if you do this, then it also causes your algorithm to converge a bit faster. So concretely, if x1 is the size of your houses, again, you can set x1 to be the size in square feet. This is, but this parentheses square feet, I just mean the size in square feet, maybe divided by 2,000 minus 0.5. And this is really, right, the size in square feet minus 1,000 over 2,000. So if the average size of the houses in your training set is about 1,000, this would cause x1 to have about 0 mean. And similarly, maybe x2 equals the number of bedrooms minus 2 divided by 4. It doesn't have to be exactly 2, subtract off some value close to the mean of x2. And if you do this, then x1 and x2 will range between, say, approximately range between minus 0.5 and positive 0.5, say. And again, it's fine if these numbers are a bit off, but the point is, if x1 and x2 have roughly 0 mean and have a range of values as about 1, then it'll usually help gradient descent converge a little bit faster. And of course, rather than plugging in the numbers, right, I had x1 minus 1,000. Oh, right, excuse me, I had size minus 1,000 over 2,000, right? Of course, rather than just plugging in the value 1,000, what you can do is take x1 and set that to size minus mu1 over s1, where s1 is a scaling factor. Similarly, x2 equals number of bedrooms minus mu2 over some other scaling factor, mu2, where I can let mu1 be the average size of the house in the training set, and mu2 equals the average number of bedrooms in the training set. And if you do this, x1 and x2 will have 0 mean, and you can choose s1 and s2. Say s1 can capture the range of the data. So for instance, you can let it be the max minus min. So the size of the largest house in your training set minus the minimum size, the smallest house in your training set. So S1 captures the range of is really right. The size of the largest house minus the size of the smallest house is the range of values, is the magnitude of the range of house sizes in your training set. Or if you know what the standard deviation of a random variable is, you can also set S1 to be equal to the standard deviation of the sizes in your training set, and S2 to be equal to similarly the standard deviation of the number of bedrooms Okay, that's assuming if you know what the standard deviation of a random variable is. But if you don't, you can just set it to this max number of bedrooms minus minimum number of bedrooms. And again, I wouldn't sweat the details of the normalizing constants mu and s1 too much, so long as you get them to be approximately comparable ranges and approximately zero mean, gradient descent will do fine. So that was feature scaling, and hopefully that will let your and this is something good to do whenever you have features for linear regression x1, x2, x3, and so on that may take on very different ranges of values. And hopefully with feature scaling, you'll be able to get gradient descent to run a little bit quicker for linear regression.